So for this video, I have written everything out, so hopefully it'll be a little faster. But we're just gonna go over all the stuff we've talked about in terms of integration, so that we can understand the disk method and the washer method better. So chapter 4, we talked about integration. This was basically our equation for integrating functions. And it just told us the area under the curve. And in 6.1, it was preparing us for 6.2, and they wanted to show us how to integrate intersecting functions. So you have two functions this time, and they're crossing, and A and B is where, and B, where f of x equals g of x. So those are the points of intersection for f of x and g of x. And what this is going to show us is this is going to give us the area between the two curves. So in chapter 4, we were talking about the area under a curve, and we'll get to what that looks like in a graph in a little bit. But chapter 4 was area under the curve, and then chapter 6.1 was area between two curves. And then we moved on to 6.2. The first half was the disk method, and you're just given one function. It's a lot like what we did in chapter 4. So we're given one function, and that function is actually going to be our radius, and we're just applying the volume of a sphere to find this. So we're rotating it around that axis, and that's going to give us the volume under the curve because it's 3 dimensions instead of just 2 dimensions. So this is if we rotate it around the x-axis, and this is if we rotate it around the y-axis. So notice how everything, when we rotate it around the y-axis, everything has to be in terms of y. And C and D are going to be where basically f of y intersects, or sorry, is basically the same boundary points as A and B. It's just the points on the y-axis instead of the x-axis. So points on the y-axis, points on the x-axis, and then that's just volume under one curve, kind of like in chapter 4. And then we went to the washer method. The washer method is a lot like the integration of intersecting functions. So we're given two different functions. This is usually f of x, this is usually g of x. And so it's kind of a combination of 6.1 and the disk method. So we are going to take f of x like we did here and subtract it from g of x, but we have to apply it to the spherical volume, the equation for finding the volume of a sphere, just like we did up here. So we have pi, and we're doing r squared, and then we're doing it times the depth. And so this is in terms of x, so when we're rotating around the x-axis, and this is in terms of y when we're rotating around the y-axis. Again, C and D for this one are going to be where f of y and g of y intersect. A and B are going to be where f of x and g of x intersect. So again, x-axis and y-axis, or points on the x-axis, points on the y-axis. So that kind of follows the same idea that we had over here, where A and B are where f of x equals g of x. So same thing here, where f of x equals g of x, where f of y equals g of y. And the washer method, more simply put, is down here. So all we're finding is we're taking the area and then we're multiplying by the depth. And as we talked about before, the depth is infinitely small. It's kind of like adding up all the rectangles underneath. So when we're talking about integration over here, and we had a line and we drew a bunch of tiny rectangles, and we can split all these rectangles in half and those ones in half and get infinitely small rectangles, and then adding them up, all of them up together, will actually give us the volume underneath the curve. So that's this, we're doing the same thing here. So d of x and d of y are that infinitely small depth. I just made a quick note down here. All of these can be in respect to the y-axis, so including these two. We kind of talked about these two a little bit more because we're rotating it around the y-axis, but all of them can be in respect to the y-axis. We just have to change from f of x to f of y, so that's very important. And a and b must be points on the y-axis. So on all of these, I represented a and b as x-axis points and c and d as y-axis points. So let's look at what it looks like on the graph. So I tried to match these up. So this is what we learned in chapter 4. This is 6.1, 6.2a, 6.2b. So again, we're trying to add up a bunch of rectangles like we talked about in chapter 4, and you can get infinitely small ones, and that's what the whole point of integration is it's basically a way to add up infinitely small rectangles underneath a curve. And so we're doing the same thing here. We're taking all these rectangles and then we're subtracting out all the smaller rectangles underneath g of x. So this is g of x, this is f of x, and we're going to get rid of all this area, and now we're left with the area that we want, which is this stuff. And again, integration is just basically adding up infinitely small rectangles. And so we're going to do the same thing here, believe it or not. We'll just look at one rectangle for now. So if I take a rectangle here, and I'm going to rotate it just like I rotated the function around the x-axis, I'm going to rotate this around the x-axis. And so what I'm left with is a disk. This is really messy, so I'm going to just draw it over here. But what happens is, take this and we rotate it around like so, rotate it back around, and we are left, since it's a rectangle, we're left with a disk like this. So it's the same idea that we had over here. So now we're going to take another rectangle. So let's say we take the one next to it, and we're just adding another disk right next to it. This one's going to be a little longer. And then we're taking another disk, because there's another rectangle there. And we're just going to keep on adding disks. And so the integration is just adding up infinitely thin disks. Just like over here, right? We're taking a bunch of disks and we're adding them up together. So if we come down here, we're going to do the same thing here where we're taking all these disks, but then there's disks given by g of x that are even smaller, and so we're just going to get rid of all the smaller ones. And then we're left with our desired, so I'm just going to color this all in blue. And now we're left, all the green stuff is the stuff that we want. So that would look like something like this. Again, or I haven't said this, but I'm not very good at art, so I'm doing my best here, but we're left with something that looks like a washer, if you've ever seen a washer before, not as in like a house appliance, but so if we look down here, the outside will look kind of like a bowl shape, and then the inside is more of a V shape, given by the g of x. So again, this is 6.1a. This is the disk method, and we're just making a bunch of disks. 6.2a, 6.2b is the same concept from 6.1, but applied to when we rotate it around the x-axis. Last thing we're going to look at right now is if we rotate it around the y. So we're going to do the same thing where so this is the disk method. I'm going to take out a disk here, and then I'm going to do another disk here, and another disk here. And basically I'm just going to add up all these disks, but what's different is I'm doing it in terms of y, and then C and D are points on the y-axis, right? C and D. And so I'm doing C to D pi, basically Fy squared dy. So that's the biggest difference, and you can see the difference right here, right? So this is the same line, just I rotated this one around the x-axis. Over here it's the same line, but I rotated it around the y-axis. This one is the same concept for the washer method. So now I'm gonna take a disk here given by g, oops, that's supposed to be y, not x. G of y, f of y. So g of y is the outside one, right? So it's further away, so I am taking g of y first, finding all the disks of g of y. I'll come down here, g of y. And then I'm taking all the disks from f of x, and I'm going to subtract out the f of x ones. So that's basically taking out this middle stuff here. So now we're left with, it's going to look like this on the outside, and then on the inside it's going to look like this. So it'll be kind of an odd shape. But this is all going away. We're subtracting out that, and what we're left with is this, basically, but in a circular bowl shape or cone shape. It's kind of funky looking. We can also do this in terms of different lines, but it's really the same concept. The only difference is when we're doing different lines, we're going to be doing, we have to subtract out the distance. So we talked about Jimmy before. Jimmy has a basketball hoop. Jimmy is 6 feet tall. Actually, let's say, yeah, Jimmy is 6 feet tall and his hands can't go above his head, so he can only reach up to 6 feet. And Jimmy's basketball hoop, just like any other basketball hoop, is actually 10 feet. And so in order to find out how high Jimmy has to jump, we're going to take the farther distance and we're going to subtract out the closer distance, and that's going to tell us how high Jimmy has to jump. So Jimmy has to jump 4 feet in the air in order to grab the rim, which is 10 feet in the air. So we're going to do the same thing if we take, say we take this function, right? We're used to rotating it around here, but let's say we rotate it around x equals 2, right? So originally we were taking from a to b r x squared, right? So this is our This is f of x. So this is our equation, right? And we just kind of plugged in f of x for r before, right? Because the radius was from this line to this line. But now the radius is from this same spot to this spot. So what we have to do is we have to change our radius, right? It's in terms of our radius, not our function. So what we're going to do is we're going to take the farther distance, which is f of x, and we're going to subtract out the lesser distance, which is 2, right? From here to here is 2. From the axis to the function is just f of x. So just like we did 10 minus 6, right? 10 minus 6 to get 4, we have to do f of x minus 2 to find the radius. From A to B. The tricky thing is, I'm going to come over here, is if we have, say we have the same function, and let's say we rotate it around x equals 6, right? So now x equals 6 is the farther distance, or is this distance, and we're trying to find this distance because that's going to be our radius, and we know this distance, f of x. So what we have to do here is, I'm going to do this one in blue, light blue. I'm going to go from A to B. This time we're going to do 6 because 6 is farther away, just like 10 is farther than 6 here. I'm going to do 6 minus f of x squared, d of x. So this is the same idea if we rotate it around a y line, right? You have to find the new radius. It's going to be a new radius. You'll know how far your original radius was from the axis, and you'll know how far the line is from the x-axis. And so you have to subtract one from the other in order to find the new radius. And again, this is the radius. It has to be the radius. It's not just the function, the radius. So hopefully this was a better way of describing it. If you want me to post, I can post these pictures or these notes. They've been a little tainted from all the drawings, but if you want me to post these, I can do that for you. And if you have questions, please let me know. This is a very tricky concept, and so the more you tell me how confused you are, the better I'll be able to help you with it.